If you were to imagine the universe as a giant city, it would not be the kind with tidy streets and neatly labeled trash cans. No, the universe is more like that one friend who insists they have everything under control while living in a house made of organized chaos. But here is the twist. This cosmic mess has a system, a strange, enormous, endlessly patient system where everything gets used again, rearranged, repurposed, or transformed into something completely different. And one of the most surprising things caught in this eternal loop is light itself. Light, the supposedly free-spirited traveler of the cosmos, the thing that zips around at the fastest speed allowed by nature, is not as free as it thinks. The universe has ways of grabbing it, bending it, twisting it, and occasionally stuffing it into cosmic storage, like a photon trying to hide from its responsibilities. Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing, but only if you enjoy these calm journeys through the universe. Now, let's begin. It is easy to imagine light as something that just leaves its source and goes on a one-way road trip across space. You can picture a lonely photon with sunglasses and a tiny cosmic backpack, hitchhiking among galaxies while humming a tune older than the Earth. But that poetic image hides a bigger truth. Light is part of a universe where nothing is disposable. It might travel unimaginable distances or survive for billions of years, but sooner or later, something will catch it. A star, a planet, a dust cloud, even the fabric of space itself will decide it needs that photon for something. In this universe, every photon eventually gets called back to duty. The cosmos has the ultimate no free lunch policy, and light is on the menu. When most people think of recycling, they picture plastic bottles or cardboard boxes. The universe laughs politely at this. It recycles entire stars. It reuses galaxies. It folds and unfolds the very energy that makes reality possible. And in the middle of all that, light becomes a kind of universal currency, exchanged, reshaped, and repurposed with a persistence that borders on obsession. Light is not just illumination. It is motion, information, heat, momentum, and sometimes even a cosmic breadcrumb trail leading back to events that happened before Earth had oceans. A photon might begin its journey as the byproduct of some violent event, say a star throwing a tantrum and fusing hydrogen atoms together. But its identity is not permanent. A billion years later, that same photon, now redder, colder, and much more bored, may end up warming the surface of a planet, tickling the antenna of a spacecraft, or disappearing into a cloud of cosmic dust like a magician at the end of a show. One of the most delightful parts of this story is that light is always honest. It cannot help itself. A photon carries the memory of what the universe has done to it along the way. When space stretches, light stretches with it. When gravity pulls on space, light bends right along. You could almost say the universe signs every photon like an autograph. Here is where I bent you. Here is where I stretched you. Here is where you almost fell into that black hole, but changed your mind at the last second. It is cosmic storytelling encoded in beams of energy. And in this giant recycling center, time itself plays a sneaky role. Humans tend to think of time as a river that flows in one direction. But in the universe, time is more like a janitor quietly working night after night, sweeping up and reorganizing everything while the galaxies whirl around above. Time stretches light, ages it, cools it, and transforms it. A photon emitted when the universe was still figuring out how to not be a boiling fog of particles is still drifting around today, carrying the universe's childhood photos like an embarrassing scrapbook it never asked to keep. What makes this even more fascinating is that light can vanish without truly being gone. When light is absorbed, the universe does not just delete it. Instead, its energy gets shuffled into another form, like cosmic budgeting. A planet might absorb sunlight and re-emit that energy as warmth. A dust cloud might catch a beam of starlight and glow with its own faint shimmer. Even a tiny atom can absorb a photon and send out another one later, like exchanging messages in a cosmic pen pal program. Nothing is wasted. Everything is transformed. If the universe had a motto, it would probably be something like reduce, reuse, recombine. So when we talk about the universe recycling everything, we are not just making a cute metaphor. We are describing a system so vast and intricate that even something as fast and slippery as light cannot escape its responsibility. The universe keeps track. It remembers. It repurposes. And it does it with a kind of cosmic humor, as if saying, "Go ahead, little photon. Run as fast as you can. I will find a way to use you again." Deep inside a star, the universe lets its inner pyromaniac run wild. It is not the peaceful, twinkling light we see from afar. Inside, it is pure, unfiltered chaos. Imagine squeezing a crowd of people into a room the size of a closet, then gradually heating that room until everyone inside becomes plasma, a seething soup of charged particles, bumping, shoving, and colliding with the energy of an argument at a family reunion. That is the core of a star. It is a place so dense and so hot that atoms barely have time to remember who they are before some other particle barrels into them at speeds that would make a race car blush. In this environment, hydrogen atoms do not behave politely. They do not wait in line. They do not gently bond. Instead, they are shoved together under immense pressure until they fuse, forced into becoming helium through a process that feels much less like a handshake and much more like a head-on collision. The universe is kind enough to reward this cosmic chaos with an outburst of energy. Fusion releases an enormous amount of light in the form of newborn photons, but these photons are not graceful beams drifting serenely out into the cosmos. Oh no, these things emerge like rowdy toddlers who have just eaten too much sugar, full of energy, bouncing off the walls, and completely unaware of the impossible journey that lies ahead. A photon born in the heart of a star is a creature of pure enthusiasm. It comes into existence with the energy equivalent of a cosmic shout, If it had lungs, it would yell something like, "Let me out." But the cruel joke is that escaping a star's core is a bit like trying to sprint your way out of a crowded concert venue when everyone else is running in the opposite direction. The density inside the core is so high that the newborn photon cannot move more than a tiny fraction of a millimeter before slamming into another particle. It is like a cosmic pinball machine, except every bumper is superheated plasma, and every collision changes the photon's direction, energy, and general sense of purpose. If photons could get dizzy, this would do it. The reality is that despite being the fastest travelers in the universe, photons inside a star live their early lives as prisoners. They are poked, bounced, absorbed, re-emitted, nudged, and redirected by a chaotic swarm of protons, electrons, and ions, all jostling for space, like commuters stuck on an intergalactic subway car. Every collision steers the photon somewhere else, like the star is constantly saying, "Nope, not that way," and smacking it sideways. The star's interior is a dense fog of particles, and a photon inside it is essentially walking blindfolded in a room full of extremely energetic elbows. This journey is not just long, it is mind-bendingly slow for something that normally zips across the universe faster than you can even say the word photon. Each time it gets absorbed and re-emitted, it loses a little of its original energy. What began as a high-energy gamma-ray photon, practically shouting with excitement, slowly, reluctantly, gets toned down through countless collisions until it becomes more like the soft, polite light that eventually escapes the star's surface. You could say stars have a way of teaching photons humility. But the most interesting part is what this chaotic journey reveals. Inside a star, photons are not just sources of light, they are the lifeblood of the system. As they bounce and ricochet, they carry heat outward, transporting the energy of the core toward the upper layers. This is the star's internal delivery system. Without photons constantly ramming their way through the chaos, stars would collapse in on themselves. In a sense, photons are the tiny messengers working overtime to keep a star alive, even though they have no idea they are doing it. They are like cosmic interns who think they are just running around aimlessly, but are actually sustaining an entire system. Every single movement inside a star is determined by physical laws that operate with the calm stubbornness of a universe that has been doing this for billions of years. The photons do not choose their direction or their fate. The plasma chooses for them. This dense environment is so extreme that it exists nowhere on Earth, not even in the most advanced laboratories. The temperatures and pressures are so intense that matter behaves in ways we can only describe with mathematical poetry. Electrons and protons dance together in a frenetic choreography, and in the middle of it all, photons are born, flung around, reshaped, and launched on a journey they will spend a very long time attempting to complete. What makes this story feel almost comedic is the contrast between a photon's nature and its situation. Light is supposed to travel in straight lines. It is supposed to be unstoppable. It is the universe's speed champion. But inside a star, light is reduced to stumbling drunkenly through a crowd of particles, that refuse to let it leave. A photon could spend hundreds of thousands, sometimes even millions of years wandering inside a star before it finally reaches the surface and breaks free into the open universe. Imagine training your whole life to run the world's fastest race, only to be trapped in a cosmic mosh pit for nearly 1,000,000 years. And when a photon finally escapes, when it finally reaches the surface of the star and bursts into the open like someone sprinting out of a maze, it emerges transformed. It is no longer the high-energy spark it once was. It is gentler, cooler, and more refined, as though the star's interior gave it an aggressive makeover. Only then does it begin the next stage of its existence, leaving behind the fusion chaos of its birthplace. It does not look back. It does not remember the 1,000,000-year labyrinth it just survived. All it knows is that at last, after unimaginable struggle, it is free. If you could shrink yourself down to the size of an atom and take a tour through the inside of a star, you would immediately regret your decision. The interior of a star is not a place designed for sightseeing. It is more like being tossed into the world's hottest, brightest obstacle course, where every obstacle is made of charged particles that move with the enthusiasm of someone who just drank too much coffee. Deep within this inferno, light is trying to do something shockingly difficult: leave. And it is terrible at it. People tend to imagine light as an elegant beam that glides effortlessly through space. But inside a star, light does not glide. It stumbles, it ricochets. It takes so many wrong turns it might as well be navigating with a map drawn by a confused toddler. Imagine the densest crowd you have ever been in, then multiply that by a few trillion. That is what photons deal with. They are surrounded by particles packed so tightly that movement becomes a game of microscopic bumper cars. A photon tries to move forward and immediately slams into an electron. It tries again and hits a proton. It shifts direction to avoid the chaos and winds up bouncing off an ion that was minding its own business. If photons had a sense of frustration, the inside of a star would be the place they discover the meaning of the word hopeless. The star's interior is thick in a way that defies everyday experience. The density is so enormous that a cubic centimeter of the core, about the size of a sugar cube, would weigh more than the heaviest vehicle humans have ever built. And this density creates a labyrinth that light cannot navigate cleanly. Instead of streaming outward in graceful lines, photons zigzag wildly. Their paths twist and turn with the unpredictability of a fly trapped in a jar, except the fly is made of pure energy and the jar is made of hyperactive plasma particles that refuse to stay still. What makes this more complicated is the temperature. A star's interior is so incredibly hot that atoms do not behave like complete, unified structures. Their outer electrons have been stripped away, leaving behind a churning mix of charged fragments. Photons trying to pass through this chaos are constantly being absorbed by electrons and then re-emitted in random new directions. It is like the universe's most chaotic version of tag, except no one keeps score and everyone gets tagged every fraction of a second. A single collision inside the star might change a photon's direction only slightly, But multiply that by countless interactions, and the photon ends up wandering in circles, loops, spirals, and strange meandering paths that defy any sense of order. A photon could attempt to move upward, but find itself shoved sideways for the next 1,000 years. It could sprint forward in one moment, and then get bounced backwards the next. If you could trace the exact path of a single photon inside a star, it would look like a scribble drawn by someone trying to sketch while riding a roller coaster. And here is the part that truly highlights how absurd this journey is. Despite traveling at the universe's fastest speed, a photon takes thousands of years, sometimes more, to get from the core of a star to its surface. It is the ultimate example of speed being irrelevant when the traffic is unbearable. A photon could be trying its hardest to move outward, but the chaos of the star keeps redirecting it, trapping it in an endless maze. It is the cosmic equivalent of being stuck inside a mall where all the exits keep moving and every hallway leads to the food court. Over time, the photon's identity changes. It starts as an energetic burst, born in the blistering heart of the star. But every collision shaves off a little of its energy. Every chaotic redirection turns the photon into something slightly calmer. The star is essentially giving it an extremely long, extremely unwanted makeover. By the time a photon finally reaches the outer layers where particles are less densely packed, it has transformed from a powerful, energetic spark into a more relaxed, gentle form of light. Only then does it finally see the cosmic equivalent of the mall's glowing exit sign. Breaking through the outer layers of a star is like suddenly stepping out of a crowd into open air. After thousands of years of collisions, redirections, and energetic midlife crises, the photon bursts into space and experiences the joy of freedom. No more being shoved around by electrons, no more surprise tackles from protons, no more wandering through an endless plasma labyrinth. It is finally free to travel in a straight line, the one thing it was always meant to do. When the photon escapes, it does not look back. There is no triumphant speech, no final farewell, no dramatic slow-motion moment. It simply leaves, rushing outward into the universe, like someone who just found the exit door of a mall they have been trapped in for centuries. The star does not miss it. It has countless more photons being born every moment, and the photon, finally liberated, races off into the vastness of space, leaving behind the only home it has ever known, a home that treated it like a hyperactive pinball for thousands of years. The incredible journey of light through a star's interior is a story of perseverance, chaos, and cosmic slapstick. It reveals how even the simplest parts of the universe, tiny packets of energy born in a fiery core, must struggle through unimaginable challenges before making their way into the open cosmos. And once they do, their journey has only just begun. When a photon finally bursts free of a star's surface, it is a moment of triumph that the universe never pauses to celebrate. There are no cosmic confetti cannons, no applause, no congratulatory message from the star that held it hostage for so long. Instead, the photon is unceremoniously hurled into open space, blinking metaphorically at the sudden openness around it. It has escaped the relentless crowd of particles inside the star, and now faces a new challenge, traversing the chilling emptiness that stretches between celestial bodies. This emptiness is not a friendly neighborhood. It is more like the world's largest, darkest wilderness, where distances are so extreme they make the concept of far away look adorable. The moment a photon enters space, it becomes one of the universe's most dedicated travelers. It races forward with absolute determination, because for the first time in its entire existence, nothing is in its way. Space is so empty that a photon can travel for billions of years without bumping into anything larger than a rogue atom. For something that has spent so long being shoved around, this freedom must feel like bliss. If a photon had emotions, it would probably shout something like, "Finally, room to breathe," which is ironic, since space has no air whatsoever. But this journey is not just a road trip. The photon is carrying information, whether it wants to or not. Its color, its energy, its direction, all of these details are messages about where it came from and what it has been through. If the universe had a gossip network, photons would be the ones spilling all the secrets. They tell us how hot their star was, how fast it was moving, whether it was wobbling from the tug of a nearby planet, and even what kinds of elements the star contained. They reveal starquakes, eruptions, rotations, and magnetic tantrums. They deliver these cosmic whispers across distances so enormous that humans have to invent new units of measurement just to keep track. The funny thing is that photons do not care what stories they are carrying. They do not try to be discreet. They do not redact sensitive information. They simply exist, flying outward at the universe's top legal speed. Every time we point a telescope at the night sky, we are essentially catching photons in the act of oversharing. A star could explode halfway across the galaxy, and a photon will run straight to us yelling, "You'll never believe what just happened over there?" They are the universe's least confidential gossip, spilling cosmic tea that is sometimes billions of years old. But there is something beautiful about that gossip. The light we see from distant stars is ancient. When you look up at the night sky, you are not seeing stars as they are. You are seeing them as they were, long before cities existed, long before humans walked the earth, sometimes long before Earth itself was even a thing. A photon that left its star while dinosaurs roamed the planet might just be reaching your eyes now, probably confused about why it traveled for so long, just to get absorbed by a creature staring open-mouthed into the night. It is a form of time travel you can do without leaving your backyard. The universe sends us messages from across its vastness, and all we have to do is look up. The journey is not always smooth, though. Space is mostly empty, but not completely. There are occasional gas clouds, dust grains, wandering planets, and the invisible tug of gravity. These do not usually stop a photon outright, but they might nudge it or stretch it, or alter its path with a gentle pull. In some sense, space is like a giant obstacle course that a photon barely notices but still has to deal with. Gravity, for example, does not block photons. It curves the space the photons are traveling through. To a photon, This feels like discovering that the straight road it was following has quietly transformed into a gentle hill without warning. It just keeps going, unaware of the subtle detours space has imposed on it. Sometimes a photon passes through a region of space filled with scattered particles. It might get redirected very slightly, not enough to stop it, but enough to whisper a new detail into its cosmic story. Space does not treat light with hostility, but it does treat it with curiosity. It molds it, shifts it, shades it, and stretches it. The universe has a habit of editing the messages it sends before they reach their destination. The most astonishing part is how patient photons are. They do not age in any human sense. They do not get tired. They do not slow down. A photon emitted when the universe was much younger can travel for billions of years without complaint, preserving the history of its birthplace with unwavering loyalty. It continues its journey until something interrupts it, perhaps a telescope mirror, perhaps a drifting asteroid, perhaps the surface of a planet that never expected to receive such ancient cargo. And when the photon is finally absorbed, its story ends, not with a dramatic finale, but with a quiet transfer of energy. It vanishes into whatever caught it, leaving behind the last whisper of a distant star. Its life is complete, though it never knew it was alive. It has delivered its message, traveled its impossible journey, and contributed its tiny piece of the universe's ongoing conversation. Starlight is more than illumination. It is a bridge between worlds, a thread connecting distant eras, a messenger that never hesitates and never forgets. It travels across the void, carrying tales of creation, destruction, and everything in between, gossiping cheerfully across the cosmos until it finally finds someone, anyone, willing to listen. The moment a photon travels into the gravitational influence of something massive, be it a star, a planet, a galaxy, or a black hole, the universe quietly steps in and says, "All right, little traveler, you are going this way now." Gravity does not grab light the way it grabs falling apples or stumbling astronauts. Instead, it tweaks the very fabric of space, reshaping the photon's path with the subtle authority of a parent gently steering a distracted child away from a busy street. If space were a sheet of fabric, gravity would be the weight placed on it, making dips and curves that any passing photon must follow, even though photons themselves have no mass. In this cosmic landscape, mass does not merely exist, it sculpts. The result is a spectacle that feels both elegant and mischievous. Massive objects bend light as if they are cosmic funhouse mirrors, stretching and twisting the glow that passes nearby. But unlike the mirrors you find at carnivals, which simply make you look taller, shorter, or vaguely like a startled giraffe, gravitational bending can reshape entire galaxies of light into arcs, rings, and streaks. The phenomenon is known as gravitational lensing, though it rarely behaves as politely as a traditional lens. Gravity lenses the way a toddler organizes toys, creatively, unexpectedly, and occasionally with startling precision. Imagine a distant galaxy sending out photons in every direction. Some of those photons travel straight toward us, while others pass near a giant cluster of galaxies that happens to be lounging in the space between. The massive cluster does not block the photon's path, it distorts it. The photon curves around the cluster, its route warped by the heavy presence of dark matter and luminous stars. From our viewpoint, the distant galaxy suddenly looks stretched, duplicated, or wrapped into glowing arcs. It is as though the universe accidentally updated its graphics settings and forgot to tell us. These arcs are more than visual curiosities. They are literal rearrangements of starlight, reshaped by the invisible hand of gravity. They are also astonishingly beautiful. Astronomers call some of these patterns Einstein rings, because sometimes the alignment is just right. Light behind a massive object, Earth in front of it, and the light gets bent in a perfect circle. It is the universe's way of showing off, crafting a piece of cosmic jewelry billions of years before anyone invented the idea of a ring. But gravitational bending does not require galaxy clusters to work its magic. Even something as humble as a star can bend passing light. Though the effect is tiny, a star's gravity, while impressive on a cosmic scale, only nudges photons a bit. It is like a gentle, polite push from a friend guiding you through a crowded room. Black holes, on the other hand, do not do polite nudging. They yank at light so intensely that they can wrap it entirely around themselves, making the region near them glow in eerie, distorted halos. If the universe had a hall of optical illusions, black holes would run the place. What makes gravitational bending so astonishing is how simple the underlying principle is. Mass curves space. Light follows space. So wherever space curves, light curves with it. There is no negotiation. Photons are extremely obedient. They do not complain. They do not get confused. They are the universe's most disciplined travelers, going exactly where the geometry of space tells them to go. To them, a curved path is not strange. It is simply the straightest possible route through a warped landscape. For observers on Earth, gravitational lensing becomes a tool for learning about parts of the universe we cannot see directly. If a massive cluster bends light more strongly than expected, it hints at the presence of dark matter, an unseen substance that does not shine, reflect, or glow, yet contributes enormous weight to the universe. The light passing by reveals its presence by bending around what appears to be nothing. In this way, photons become accidental detectives, tracing the shape of gravity itself and outlining structures no telescope could otherwise observe. Even more intriguingly, gravitational bending can magnify distant objects. A galaxy that would normally be far too faint to detect suddenly becomes brighter, stretched by gravity's funhouse mirror, into a shape we can spot with our instruments. This allows astronomers to peer deeper into the universe, catching glimpses of ancient stars and galaxies that would otherwise remain hidden. Gravity becomes a cosmic magnifying glass, and light becomes the story it enlarges. To the photon, though, none of this feels dramatic. As it passes by a massive object, it experiences no jolt, no sudden yank, no sense of veering off course. It simply continues forward at the speed of light, following the straightest possible path that space allows. If photons had consciousness, they might be baffled to learn that astronomers on a distant planet are studying their curved trajectories as evidence of invisible matter. They might say something like, "I was just following the road. You are the ones drawing conclusions." Yet the bending of light is one of the universe's most elegant truths. It reveals a cosmos that is not static, but sculpted, not rigid, but flexible. Space behaves less like an empty stage and more like a vast fabric that responds to every ounce of mass and energy. Light becomes the thread that reveals the contours of this fabric, tracing invisible shapes with unwavering loyalty. In the end, gravitational fields are not merely obstacles or detours for photons, they are artists. They stretch, curve, and reshape the glow of the universe, creating patterns written not by hand, but by mass itself. Through these distortions, the cosmos tells a story about its hidden structures, its ancient weight, and the way all things, matter, energy, and even the empty spaces between, are intertwined in a single astonishing design. When starlight drifts into the great expanses of interstellar space, it expects an easy journey. After all, space looks empty, a quiet, peaceful highway stretching endlessly in all directions. But hidden in that supposed emptiness are vast clouds of dust and gas, the cosmic equivalent of fog banks large enough to swallow entire star systems. These dust clouds are not the soft, gentle dust you swipe off a bookshelf. They are made of microscopic shards of carbon, silicates, and frozen molecules that drift through space like ancient confetti from the universe's earliest celebrations. And when light enters these clouds, things start to get wonderfully complicated. Dust clouds do not treat light with the kind of respect photons might expect after traveling across the galaxy. Instead, they catch it, block it, scatter it, and sometimes transform it into something completely new. A photon entering a dust cloud might imagine it is just passing through a faint mist, but it is actually stepping into a cosmic art studio where the universe keeps its leftover materials and occasionally decides to paint something stunning. The captured light begins to bounce around inside the cloud, colliding with tiny grains like a hyperactive pinball. Unlike the chaotic collisions inside a star, this scattering is gentler, but it still redirects photons in every imaginable direction. Some get sent deeper into the cloud, swallowed by darkness like they have stumbled into the wrong neighborhood. Others scatter outward, illuminating the cloud from the inside and giving it the soft glow that astronomers adore in nebula photographs. These glowing regions are not just pretty. They are recycling centers where old starlight gets repurposed into a brand new spectacle. Some nebula shine because they reflect light from nearby stars. These are called reflection nebulae, and their beauty lies in their subtlety. They do not produce light themselves. They simply redirect what they capture, like a cosmic mirror made from dust grains instead of glass. When a photon hits one of these grains, it bounces off at a new angle, and enough of these reflections turn the entire nebula into a softly glowing cloud. It is as if the universe took a bucket of starlight and lightly brushed it across a canvas made of dust. Other nebulae take a more dramatic approach. Instead of merely reflecting light, they absorb it. When a dust grain or gas molecule swallows a photon, the energy does not disappear. It gets converted into heat or re-emitted as a new photon of a different color. This process can transform high-energy radiation into gentle red light, giving some nebulae their warm, ruby-like glow. These emission nebulae look like the universe dipped its brush into a jar labeled volcanic sunset and went wild. One particularly theatrical example of this recycling is the glowing hydrogen clouds scattered throughout our galaxy. Hydrogen atoms, when excited by energetic starlight, release their own characteristic red glow. These glowing regions trace the outlines of stellar nurseries where new stars are forming from collapsing gas. The dust and gas do not merely decorate space, they reveal, through their shimmering light, where the next generation of stars is being born. It is like seeing a construction site illuminated by the very energy that will one day burst forth as brand new starlight. And then there are dark nebulae, the introverts of the cosmic neighborhood. These clouds are so thick with dust that they block nearly all light, leaving behind eerie silhouettes that stand out sharply against the glow of surrounding stars. They do not reflect light, they hoard it. They do not glow, they consume. But even in their darkness, they play a crucial role. They are where stars begin. The dust and gas inside them collapse under gravity until the central regions ignite into new suns. These nebulae are less like artworks and more like the universe's backstage curtains, hiding the dramatic rehearsals that precede stellar birth. Despite their varying personalities, all nebulae share one truth. They are masters of light recycling. They take photons that would otherwise rush through space unimpeded and turn them into glowing displays that stretch across dozens of light years. The Blue Horsehead Nebula, the Orion Nebula, the Eagle Nebula, each one is a monument to the universe's habit of taking light. It finds lying around and doing something creative with it. If you could walk through a nebula, you would see dust grains floating silently in all directions, scattering beams of light into ethereal patterns. It would feel like strolling through a painting that is constantly shifting, constantly rewoven by drifting particles and passing starlight. The dust itself, humble though it seems, is essential to the universe's creativity. These grains often begin as fragments blown out from dying stars. Supernova explosions scatter the ashes of once brilliant suns across space. Over millions of years, these ashes clump together into clouds that then reshape the light of newer stars. In this way, dying stars help illuminate future generations, turning their remnants into tools the universe uses to sculpt beauty. Light from one star might be reflected by dust created in the death of another, a cosmic collaboration spanning eras. Even more remarkable is how these dust clouds slowly change. Radiation from nearby stars can heat the dust, causing it to glow in faint infrared hues. Winds from newborn stars carve cavities and pillars in the clouds, reshaping them into iconic structures like the pillars of creation. Over time, a single dust cloud might evolve from a dark, light-swallowing shape into a radiant beacon, then collapse into a cradle of new stars, and finally disperse entirely. Throughout this transformation, light remains the artist's tool, sculpting the shape, revealing the details, and providing the color. In a universe where nothing is wasted, dust clouds prove that even leftovers can become masterpieces. They take stray photons, scattered remnants, and drifting fragments, and turn them into nebulae that shine like the universe's own gallery of cosmic paintings. Each glowing cloud is a reminder that light never stops finding new ways to surprise us, and that even the universe loves to recycle in style. Long before stars existed, before galaxies spiraled into elegant arms, before space acquired any real sense of style, the universe was a hot, overcrowded mess. Imagine every particle, photon, and stray bit of energy packed together in a single seething mass, all of them bumping elbows in an expanding cosmic waiting room. It was not majestic. It was not picturesque. It was more like the universe's middle school yearbook photo, overwhelming, slightly embarrassing, and definitely not something it expected anyone to look at billions of years later. Yet, that is precisely what cosmic microwave background radiation is. The faint, ancient glow from the universe's awkward beginnings, stretched thin across all of space. In those early ages, the universe was so hot and dense that light could not travel freely. Photons bounced constantly off electrons and protons, unable to move more than a tiny distance before being deflected again. The universe at this stage was not transparent. It was a fog of glowing plasma. You could not have seen anything because seeing requires light to travel in straight lines, and straight lines simply did not exist then. Light was trapped, restless, and thoroughly annoyed. But as the universe expanded, it cooled. Cooling meant electrons could finally settle down and bond with protons to form neutral atoms. This transition unlocked something profound. Light could finally escape. Suddenly, photons were free to move without constant interruption, like kids finally allowed out of a crowded classroom into the quiet hallway beyond. This great release happened roughly 380,000 years after the universe began, an age that sounds young on a cosmic timeline, yet represents a monumental shift in the history of everything. Those newly freed photons scattered into the void, carrying with them a final snapshot of what the universe looked like at that moment. The density, the temperature, the tiny clumps that would one day become galaxies. And they have been traveling ever since, stretching as space expands, cooling as wavelengths grow longer, whispering a story older than every star we have ever seen. Today we detect that ancient light not as visible illumination, but as a faint microwave signal that fills the entire sky. It is astonishingly uniform, but not perfectly so. That tiny imperfection is crucial. It contains the seeds of cosmic structure. The slight, warm and cool spots in the cosmic microwave background reveal where matter was unevenly distributed in the early universe. Those small clumps, and we are talking differences in temperature so small they make a whisper sound like an explosion, eventually pulled more matter toward themselves under gravity, forming the large-scale structures we now see. Clusters of galaxies, filaments of gas, and vast cosmic voids. This microwave radiation is the oldest light we can observe. It is the universe's baby picture, though calling it a picture is generous. It is more like listening to the static of an old radio and discovering that hidden inside the crackles is a message from before Earth existed. When scientists point sensitive instruments at the sky and tune into that faint hum, they are essentially eavesdropping on the earliest conversation the universe ever had with itself. What makes this radiation even more compelling is how incredibly diluted it has become. Those photons started out with fierce energy, but time and expansion have stretched them until their wavelengths are now thousands of times longer. What was once a blazing glare is now a gentle microwave whisper. It is as if the universe's first scream mellowed into a sigh over billions of years, yet the information remains intact. The photons may be tired, but their memory is flawless. If you could somehow see the cosmic microwave background with your own eyes, never mind the fact that eyes do not detect microwaves, it would not look like a photograph in the traditional sense. Instead, it would appear as an all-sky glow, nearly uniform, with subtle blotches representing slightly warmer or cooler regions. Those blotches are the fossilized fingerprints of quantum fluctuations magnified to cosmic scales. Tiny wiggles in the energy field of the early universe, amplified by expansion, now serve as the blueprint for galaxies. One of the strangest things about this ancient radiation is how unavoidable it is. No matter where you look, no matter how deeply you peer into the cosmos, the microwave background is there. It wraps around the universe like wallpaper you cannot peel off, a relic from a time before even the first star flickered into existence. You could say the cosmic microwave background is the universe's version of an old voicemail message left on repeat, one it forgot to delete, but which turned out to contain vital evidence about its earliest days. Even more astonishing is how smooth the radiation appears. This uniformity tells us that distant regions of the young universe, regions that should not have had time to communicate or influence each other, somehow started with nearly identical conditions. This puzzle helped inspire the concept of cosmic inflation, a rapid expansion that stretched the universe faster than light could travel. Inflation took the tiny, fluctuating universe and ballooned it outward so swiftly that its wrinkles became gently smoothed out patterns we now detect in the microwave background. Every photon in this ancient glow is a survivor of cosmic history, older than galaxies, older than the solar system, older than the atoms in your body. They have drifted through space for almost 14 billion years, untouched except by the slow stretch of expanding space itself. They are the universe's longest-running travelers, passing silently through everything, humming softly like an ancient choir with notes too low for human ears. The cosmic microwave background is not just recycled light. It is light that has been stretched, softened, transformed, and preserved across the totality of cosmic time. It is the universe's way of saying, "Here is where I began, awkward and glowing and full of potential." And thanks to these ancient photons, we can listen to that first message and learn how everything that exists today began its journey in the quiet hum of the universe's earliest dawn. For all their dramatic reputation, black holes are surprisingly methodical. They do not stomp around the universe swallowing everything in sight. They do not crawl after stars with malicious intent. They simply sit in space like cosmic potholes, waiting for anything: gas, dust, light, the occasional confused particle, to wander too close. Yet despite their quiet demeanor, black holes have an undeniable flair for the theatrical, especially when it comes to light. They treat photons with the same calm finality that a vacuum cleaner treats cookie crumbs, but with one important twist: what goes in does not always stay quiet. In the environment around a black hole, light undergoes some of the most bizarre transformations the universe has to offer. To understand how black holes recycle light, imagine approaching one from a safe distance, far enough that your atoms do not get any terrible ideas about relocating. From afar, a black hole does not look like much because it does not emit light. What you see instead is the chaos swirling around it, the accretion disk. This disk is made of gas and dust spiraling inward, heating up as friction and compression push the material toward temperatures that would make the surface of a star say, "Okay, that is excessive." As this disk glows, it releases enormous amounts of light, but that light has to navigate the warping geometry around the black hole. Gravity near a black hole is not just strong, it is reality bending, path twisting, time stretching strong. Space curves so severely that photons passing nearby must trace curved routes, bending toward the black hole like iron filings around a magnet. Some light gets caught in orbits, circling the black hole again and again. These orbits are unstable, like running laps around a pit, but while they last, they create a faint halo called the photon sphere. Light here is trapped in a desperate marathon, looping until the slightest disturbance sends it spiraling inward. Even photons that escape this region do not escape unchanged. Time itself is distorted so dramatically that any light climbing out of the gravitational well becomes stretched, losing energy as it goes. This stretching is known as gravitational redshift. To a photon, it is like trying to climb a steep hill with an ever-growing backpack. It reaches the top, weaker, softer, redder. If you could sit at a safe distance and watch photons escape the vicinity of a black hole, it would look as though the light is sighing as it travels, weighed down by the intensity of the experience. But things get even more dramatic for the photons that venture too close. At the event horizon, the boundary beyond which nothing returns, light reaches a point of no comeback. Once a photon crosses this horizon, its story ends. It cannot bounce, reflect, or travel any further. Space itself carries it inward, pulling it deeper until it joins the black hole's contents. Yet even here, the universe does not simply delete the photon's existence. Its energy gets absorbed into the black hole, adding infinitesimally to the black hole's mass. It becomes part of the growing gravitational presence, a tiny contribution to the cosmic heavyweight lurking in the dark. However, black holes have a surprising habit. Sometimes, instead of quietly absorbing everything, they fling matter and energy outward with unimaginable force. These are the relativistic jets, towering beams of particles and radiation shooting out from the regions above and below the black hole's poles. The jets are not emitted from inside the event horizon. Nothing escapes from there. Instead, they are powered by the churning chaos just outside it. As material in the accretion disk swirls, twists, and compresses, magnetic fields become tangled and amplified. The black hole spins, dragging space itself around with it, and the magnetic fields channel energy upward and outward. Some of the trapped light and radiation is swept up in this magnetic maelstrom and expelled into space at nearly the speed of light. These jets are cosmic pressure washers, spectacular, focused outbursts that blast radiation across thousands, sometimes millions of light years. Galaxies hosting supermassive black holes can develop jets so enormous they stretch far beyond the galaxy itself, like someone decided to attach headlights to the universe and point them directly at intergalactic space. The material in these jets includes photons that were once trapped and stretched near the event horizon, now hurled across the cosmos with the enthusiasm of fireworks, fueled by gravity and magnetism. What makes these jets even more fascinating is that they recycle light in a way no star or nebula ever could. Photons that would otherwise be eaten by the black hole get caught in magnetic fields and launched outward, their energy amplified by the intense environment. Once expelled, this radiation can heat distant gas clouds, trigger star formation, or illuminate entire regions of intergalactic space. Black holes, despite their reputation as cosmic hoarders, turn out to be surprisingly generous with recycled energy. Even the light that never reaches the jets still leaves behind a signature. As photons orbit, stretch, or fall into the black hole, they create distortions that allow astronomers to map the warped geometry of space itself. When we observe the swirling glow around a black hole, we are seeing light that has been twisted into shapes no other object in the universe can create. The famous images of black holes, those eerie glowing rings, are made entirely of photons that traveled through wildly curved routes before finally reaching our telescopes. The black hole acts like a cosmic sculptor, shaping the paths of photons into a perfect glowing outline of its own shadow. In the end, black holes do not simply destroy light. They reorganize it, they stretch it, twist it, trap it, and occasionally fling it across the cosmos with theatrical flair. They are the universe's most extreme recyclers, turning the energy of swallowed photons into some of the most powerful and awe-inspiring phenomena in existence. Through their unstoppable gravity and roaring jets, they transform light in ways that reveal the very structure of space-time and remind us that even in the darkest regions of the cosmos, light never stops finding surprising new roles. Galaxies may look serene from afar. Those elegant spirals, those glowing cores, those shimmering halos that seem to hang in space like cosmic chandeliers. But do not let the beauty fool you. A galaxy is not a calm place. It is more like a colossal recycling facility disguised as a work of art. Behind the glowing patterns and graceful curves is an ecosystem constantly tearing things apart and stitching new things together, all while juggling light like a magician running a very busy show. If the universe had neighborhoods, galaxies would be the bustling cities where energy gets shuffled, matter gets reprocessed, and light keeps changing jobs without ever taking a vacation. The recycling begins with starlight being absorbed by dust, gas, and cosmic debris that fill every galaxy. These materials act like the universe's version of old warehouses, huge spaces filled with raw resources waiting to be reworked. A beam of starlight might travel through the spiral arms of a galaxy and find itself running headfirst into a wall of hydrogen gas, or burying itself inside a patch of dark dust. When that happens, the light does not simply evaporate. It is absorbed, its energy stored temporarily in molecules and atoms that vibrate, warm up, and eventually release new radiation. The original photon might disappear, but its energy gets re-emitted in a completely different form. Infrared light, for example, or a soft glow that radiates gently across space. This continuous absorption and re-emission make galaxies glow with multiple layers of light. Some of this glow is bright and visible, the kind of light that reaches your eyes when you look at the Milky Way on a clear night. But much of it is hidden, emerging in wavelengths the human eye cannot detect. If you could see a galaxy in infrared, it would look like a bonfire disguised under blankets, its warmth seeping through every dusty corner. In ultraviolet, it would blaze like a neon sign announcing the birth of new stars. In radio waves, it would hum with the echo of countless interactions happening in the shadows. A galaxy is not a single light source. It is a choir of wavelengths, each one carrying energy that has been recycled again and again. The true heart of a galaxy's recycling system lies in its star-forming regions. These are the colossal nurseries where new stars ignite from the raw materials collected over billions of years. They exist in giant molecular clouds, vast dark regions filled with cold gas and dust, so thick that light struggles to get through. Gravity works its quiet magic, pulling the material inward, squeezing it tighter and tighter until the pressure becomes so intense that hydrogen atoms begin to fuse. A new star lights up, bathing the surrounding cloud with radiation and carving glowing cavities in the darkness. The newborn star does not shine alone. It illuminates the remains of the cloud that formed it, turning the leftover dust into a luminous canvas. But the recycling process does not end with the star's birth. Far from it. As the young star grows, it emits fierce radiation and powerful stellar winds that blast away nearby gas. Some of that gas gets heated and glows brightly before cooling and falling back into the cloud. Some gets pushed far enough that it drifts into other parts of the galaxy, carrying with it the energy it absorbed. Light that originated inside the star might end up spread across an entire region, bouncing between dust grains, settling into molecules, and being re-emitted countless times. By the time it leaves the galaxy, that energy has taken a tour almost as long and complicated as the galaxy's own history. Even stars themselves participate in the recycling of light. Over millions or billions of years, stars expand, shed material, shrink, flare, pulse, and in some cases explode. A dying star may release its outer layers into space, scattering dust and gas, enriched with the elements it created during its lifetime. These materials eventually cool and collapse into new star-forming regions. They also absorb and emit light along the way. A photon that once warmed the outer atmosphere of a dying star might later pass through a cloud made of that same star's remains, only to be absorbed and re-emitted by a newborn star forming from those very remnants. It is recycling on an interstellar timescale, an endless loop where light never stops being reassigned to new roles. Galaxies even recycle light through their overall motion and structure. Spiral galaxies, for example, funnel gas inward along their swirling arms, creating waves of star formation that move like slow-motion fireworks. Elliptical galaxies, dense and old, glow with the accumulated light of ancient stars and the faint warmth of dust that has been absorbing radiation for ages. Irregular galaxies, the wild children of the cosmic family, scatter light in unpredictable patterns as their chaotic shapes collide with others. Every galaxy handles its recycling differently, but all of them do it constantly and ceaselessly. Perhaps the most remarkable aspect of galaxy-scale recycling is how efficient it is. Not a single photon's worth of energy is wasted unless it escapes into intergalactic space. Even then, it may eventually be picked up by another galaxy drifting thousands of light years away. The cosmic web ensures that galaxies are not isolated recyclers. They share their light, exchange material, and sometimes collide outright, mixing their contents and starting the process over again on an even grander scale. Colliding galaxies create tidal tales of stars and gas, shock waves that ignite new star clusters, and glowing regions where dust gets so thoroughly heated that it radiates like an oven turned to its highest setting. In these cataclysmic mergers, light gets torn apart and remade with explosive enthusiasm. So when you look at a galaxy in the night sky, you are not just seeing a distant island of stars. You are witnessing a vast recycling hub in action, a place where light is created, captured, repurposed, reshaped, and sent outward with renewed brilliance. Galaxies are where the universe keeps rewriting its luminous stories, making sure that every photon finds a new purpose, a new journey, and a new way to shine. When sunlight reaches a planet, it is not merely lighting up the scenery like a cosmic spotlight. It is clocking in for work. Planets are remarkably efficient at squeezing every possible use out of the starlight they receive. They warm it, redirect it, store it, transform it, and sometimes even throw it back into space dressed in new colors. Sunlight becomes the raw currency that drives everything from swirling storms to drifting continents to the forests that rise and fall over geological ages. If light had hopes of an easy retirement after its long journey, planets would disappoint it. Once starlight hits a world, its job has only just begun. The first task sunlight takes on is shaping climate. Planets receive light unevenly. Some regions get direct beams while others get it filtered, angled, diluted, or blocked entirely. Because of this uneven distribution, sunlight becomes the engine behind winds, seasons, ocean currents, and long-term climate cycles. When sunlight heats the ground or ocean, that warm surface transfers heat to the air above it. Warm air rises, cold air sinks, and suddenly the atmosphere becomes a planetary-scale dance floor where air currents swirl, twist, and sweep across continents. Every breeze, from a gentle afternoon wind to a roaring monsoon, traces its lineage back to ancient starlight that happened to land unevenly on a spinning, tilted sphere. Even a planet's tilt, a simple geometric quirk, decides how sunlight choreographs the seasons. When one hemisphere leans toward the star, sunlight arrives at a more direct angle, spreading less thinly across the surface. The hemisphere warms, plants bloom, animals wake up, and afternoon shadows shrink like someone turned up the cosmic thermostat. Half a year later, the same region leans away, and sunlight arrives at a glancing angle stretched across a wider area. Winters form not because the planet is farther from the star, but because the star's energy is smeared thin. All of this happens because the planet is constantly redistributing the sunlight it receives, storing it, releasing it, and converting it into motion. Beyond climate, sunlight becomes the architect of ecosystems. Plants, algae, and photosynthetic microbes take sunlight and turn it into chemical energy, effectively trapping photons inside bonds of carbon and hydrogen. It is a clever trick. Starlight becomes stored energy, tucked away in leaves, roots, fruits, and even tree trunks. A forest is, in one sense, a very organized warehouse of starlight. Each tree stands tall because years of sunlight have been quietly woven into the cellulose of its cells. The food chain itself is built on this transaction. Sunlight becomes plant tissue. Plant tissue becomes fuel for herbivores. Herbivores become fuel for predators. Predators eventually return to the soil, where the cycle begins again. The entire process is a remarkably elegant recycling program powered by the patience of photons. Sunlight also shapes the landscapes on which those ecosystems grow. Over long periods, differences in heating contribute to patterns of rainfall, the slow carving of rivers, and the formation of deserts and grasslands. Mountain ranges catch sunlight unevenly, heating their slopes in ways that create swirling wind systems and local weather variations. Vast, sun-warmed oceans create storms that churn moisture across thousands of miles. Every geographical feature, from a rainforest valley to a windswept plain, owes some part of its identity to how sunlight was absorbed, bounced, or stored beneath it. Even frozen worlds participate in the recycling. On icy planets or moons, sunlight may be too weak to warm the ground significantly, but its energy still matters. It can trigger sublimation, ice turning directly into vapor, or drive faint, delicate atmospheric currents. These small processes influence frost patterns, surface chemistry, and even long-term climate cycles that depend on how much sunlight the ice reflects. The shimmering, reflective brilliance of icy surfaces is part of a feedback loop. More reflected sunlight means cooler temperatures, more ice formation, and even more reflectivity.
Sunlight becomes part of a planetary conversation that continues for eons. Then there are auroras, the light shows planets put on when sunlight's energy, carried by the solar wind, meets a magnetic field. Auroras are not created by direct sunlight, but by particles launched from the star, carrying energy originally forged in its turbulent layers. When those particles collide with a planet's magnetic shield, they get funneled toward the poles, where they slam into atmospheric atoms. These atoms light up in vibrant greens, reds, purples, and blues. It is as if the planet took sunlight apart, rearranged it atom by atom, and then reassembled it into a shimmering ethereal display. Someone watching an aurora is witnessing a world recycling the star's energy into a luminous celebration. Sunlight even molds the long-term character of a planet's atmosphere. Energy from the star breaks apart molecules, rearranges them, and occasionally transforms them entirely. On some worlds, this process creates protective ozone layers. On others, it strips atmospheres away. Starlight can warm a greenhouse gas just enough to trap more heat, amplifying its influence. It can stir up chemical reactions in clouds, producing hazes that color the sky in strange, exotic hues. A planet's atmosphere is not merely warmed by sunlight, it is sculpted by it. And perhaps the most enchanting part of the whole system is how sunlight becomes embedded in time. The energy that warms the ground today may have taken millions of years to leave the star, then spent only a fraction of a second passing through space before landing on a leaf or a wave. Yet once absorbed, that same energy can remain present in a seed, a gust of wind, a drifting cloud, or the flicker of a firefly's glow. Light becomes weather, life, movement, and color. It becomes the heartbeat of the planet. So when you look at a world bathed in daylight, you are seeing a complex, layered process of recycling. Sunlight being captured, converted, stored, released, and transformed into everything from gentle breezes to towering forests. Planets are not passive recipients of light. They are active recyclers, turning starlight into the motion of air, the growth of living things, and the shimmering displays that make a world come alive. When sunlight lands on a leaf, it has no idea it is about to be kidnapped. The leaf does not look like a prison, but in the grand drama of the natural world. It is the universe's most efficient energy trap. Inside that leaf sits a dazzling chemistry lab, a microscopic factory staffed by molecules that have evolved the uncanny ability to take sunlight, swallow it whole, and turn it into food.
It is one of the most elegant magic tricks nature performs, and it goes by a name that sounds almost too simple for what it accomplishes: photosynthesis. At its heart, photosynthesis is the art of turning light into life. Plants do not just bask in sunlight the way animals bask in warmth. They grab photons and use them as currency. Every leaf is packed with pigments, the most famous being chlorophyll, which specializes in catching certain colors of sunlight. When a photon hits a chlorophyll molecule, it excites the molecule's electrons, filling them with energetic potential. It is like handing someone a cup of espresso and watching them sprint across the room with renewed enthusiasm. But unlike an over-caffeinated human, the chlorophyll does something far more organized with its energy burst. It passes it down a chain of molecules in a perfectly choreographed sequence. This chain is known as the electron transport system, and even though it sounds like something you might board at a futuristic airport, it is simply nature's conveyor belt for energized electrons. As the electrons move along, their energy powers tiny molecular machines that help split water molecules apart. Yes, every leaf is casually tearing water to pieces at the atomic level. The oxygen atoms left over from this process get released into the air, which is extremely polite of plants considering countless animals, including humans, depend on that oxygen to stay alive. Plants do this constantly without ever sending an invoice. The hydrogen components of water, meanwhile, do not get wasted. They get routed into chemical reactions that help build sugar molecules. And this is where the real magic happens. The plant uses sunlight to forge chemical bonds between atoms of carbon and hydrogen. These bonds act like tiny rechargeable batteries made of sunlight itself. The sugars formed, glucose being the most famous, are essentially edible sunlight. They store the energy of photons in a form that can be consumed, transported, stashed away, or burned later for fuel. When you bite into a piece of fruit or a vegetable, you are literally tasting sunlight that has been neatly folded into biological fabric. This conversion of light into sugar forms the foundation of nearly every food chain on Earth. Plants create sugar. Animals eat plants. Other animals eat those animals. And the energy moves up the chain like an inheritance that never stops being useful. Even creatures that have no interest in plants, wolves, owls, sharks, owe their energy to the sunlight locked away in the bodies of the prey they consume. The entire tree of life leans heavily on those first molecules that learned how to capture photons and turn them into nutrition. Photosynthesis even shapes entire ecosystems by deciding where energy flows and where it does not. Tropical rainforests, flooded with sunlight, burst with vegetation and wildlife because there is an endless supply of photons to capture. Deep ocean zones, deprived of sunlight, rely on scraps drifting down from above or unusual chemical sources. On land, moment-to-moment sunlight can dictate everything from when flowers bloom to when grazing animals migrate. In forests, sunlight becomes a currency of competition. Trees stretch taller, leaves angle themselves with precision, and vines twist their way upward in an effort to access the most precious commodity the planet offers. Even the structure of plants themselves is tailored for optimal photon capture. Leaves arrange themselves to reduce shading. Some plants track the sun across the sky.
Others grow in spirals or fractal patterns that maximize surface area. Nature experiments constantly, refining its ability to trap light with strategies that range from the pragmatic to the downright flamboyant. Just look at sunflowers turning their bright faces across the sky like cosmic solar panels with attitude. Photosynthesis does not just shape life, it shapes the planet. Over millions of years, photosynthetic organisms dramatically altered Earth's atmosphere, turning it from a hostile mixture of gases into the oxygen-rich blend we breathe today. Long before forests existed, tiny photosynthetic microbes in ancient oceans began releasing oxygen into the water and air, changing the chemistry of the entire world and opening the door for complex life. Without these early sunlight harvesting pioneers, there would be no animals, no trees, no insects, no humans, just an empty world quietly simmering under alien skies. The influence of photosynthesis reaches into geology as well. Massive deposits of coal, oil, and natural gas are essentially ancient sunlight trapped in the remains of long-dead plants and algae. These fossil fuels represent millions of years of stored sunlight that the planet once tucked away underground. When burned, they release that ancient solar energy back into the atmosphere, reshaping climates and fueling civilizations. It is one of the strangest truths about modern life. Entire human societies run on the long-stored photosynthetic efforts of plants that lived and died eons ago. Even today, photosynthesis continues to evolve. Some algae perform exotic variants of the process that allow them to thrive in extreme environments. Certain bacteria harvest sunlight using pigments that absorb wavelengths plants cannot touch. Even corals participate in a photosynthetic partnership, hosting algae inside their tissues that supply them with food. Underwater reefs owe their explosive color and life to sunlight, being recycled through these microscopic guests. So when you see a leaf glowing green in the sun, or watch a field of grass swaying in the afternoon breeze, remember that you are looking at one of nature's greatest achievements, the ability to take raw starlight and fold it into the edible, breathable, livable energy system that sustains an entire planet. Photosynthesis is the ultimate recycling trick, one that traps sunlight in snack form, feeds the world, sculpts ecosystems, reshapes atmospheres, and ensures that wherever light falls, life has a chance to rise. Humans have always been fascinated by light. Long before science explained what photons were, people noticed that sunlight warmed their skin, fire illuminated dark caves, and reflections danced across pools of water in ways that seemed almost mischievous. Eventually, curiosity turned into experimentation. Experimentation turned into engineering, and engineering turned into something remarkable: the ability to catch photons on purpose and make them work for us. Unlike plants, which quietly mastered photon wrangling billions of years ago, humans took the scenic route, but once they figured out the trick, they built an entire technological world powered and informed by the behavior of light. Solar panels are one of the clearest examples of this modern mastery. At first glance, a panel looks like a shiny rectangle lounging on a rooftop, doing little more than sunbathing. But beneath its calm exterior lies a precision-built trap designed to snatch photons the moment they arrive. Solar panels are made of semiconductor materials, usually silicon, with an internal structure arranged so that incoming photons can knock electrons loose. Each freed electron becomes part of an electric current, which humans then route into homes, batteries, factories, or electric vehicles. Every time your phone charges from a solar-powered outlet, it is running on the energy that once launched itself across space as sunlight. Solar panels are like cosmic converters, taking packets of light that have traveled millions of kilometers and persuading them to help run a kitchen toaster. The elegance of solar technology lies in its simplicity. Catch a photon, knock loose an electron, collect the motion of these electrons, and you have electricity. But achieving this took decades of refinement. Engineers had to learn how to tune the material so it absorbed just the right wavelengths. They had to stop defects from stealing the electrons. They even had to figure out how to keep panels cool, because ironically, the sun's heat can make them less efficient. Each panel is a carefully crafted balance of physics and practicality, a reminder that even though photons are tiny, trapping them requires a big effort. But humans do not use light only as a source of energy. They also use it as a messenger. Fiber optic cables, the glass-thin threads that now carry most of the world's internet traffic, are essentially long photon racetracks. Instead of sending electrical signals through copper wires, which can lose speed or weaken over long distances, fiber optics rely on light bouncing down transparent strands like a marathon runner sprinting through a polished tunnel. A single fiber can carry billions of pulses of light per second, each one encoding information, messages, videos, navigation data, financial transactions, the entire chaotic flow of digital life. What makes fiber optics miraculous is that photons barely tire. While electricity suffers from resistance and heat, light glides effortlessly through the fiber, reflecting internally in a controlled zigzag that keeps it moving forward. This means a pulse of light can travel across oceans with only occasional boosts from amplifiers. Humanity has essentially wrapped the planet in glowing spider silk, using photons to whisper across continents faster than any messenger in history. If you send a message to someone on the other side of the world, the photons carrying your words travel through cables draped across the ocean floor. Deep, cold pathways that look like something out of a sci-fi novel, yet are absolutely real. Light also helps us observe and measure reality with astonishing precision. Lasers, beams of perfectly coordinated photons, are used in everything from supermarket scanners to delicate medical surgeries. A laser works by forcing photons to march in step, each one identical in wavelength and phase. This precise coordination allows lasers to cut, measure, and encode data in ways that regular light cannot. In laboratories, lasers trap tiny particles, manipulate atoms, and even cool matter to temperatures close to absolute zero. Humans may not have invented photons, but they have certainly learned how to deploy them like tools in a cosmic workshop.
Even the screens on phones and computers rely on light manipulation. Display technologies bend, filter, and combine photons into patterns that trick our eyes into seeing colors, shapes, and movement. Each pixel is a tiny stage where photons perform in perfect choreography, switching on and off in rhythms too fast for the human mind to consciously track. When you watch a video, you are really watching armies of photons deliver visual instructions in a fraction of a second. Cameras reverse the process, capturing light instead of emitting it. Modern sensors, made of layers of silicon, convert photons into electrical signals that form digital images. The same principle allows telescopes on Earth and in space to collect faint, ancient light and decode it into maps of galaxies and nebulae. Human technology both emits and receives light, creating a constant two-way conversation across distances ranging from microscopic to astronomical. And then there are the truly futuristic innovations. Scientists are experimenting with solar paints, coatings that might someday turn entire buildings into energy harvesters. Quantum computers aim to use photons to store and transmit information with unmatched speed and security. Some research teams are exploring photonic chips, which would replace electrical currents with beams of light inside computers, leading to machines that process information at unprecedented rates with incredibly low heat. All of this represents humanity's evolving relationship with light. At first, people merely admired it. Then they copied nature's strategies, tinkered, experimented, and discovered how to bend photons to their will. Today, light powers homes, carries secrets, reveals distant stars, fuels technologies, and networks the entire world together. Every solar panel humming on a rooftop, every glowing screen, every internet connection, every laser scan at a grocery store is a quiet reminder that humans have learned not just to use light, but to repurpose it. They have turned photons into workers, messengers, architects, and entertainers. In the grand tradition of cosmic recycling, humanity now participates fully, catching light, shaping it, redirecting it, and letting it carry the creations of human imagination across the world at the speed of wonder. When imagining the far future, it is tempting to picture sleek starships, shimmering cities, or planets wrapped in neon rings. But there is something even more intriguing to consider. What if future civilizations decide that light itself is their favorite raw material? Not just for energy, not just for information, but as a medium, something they sculpt, redirect, and repurpose with the same creativity artists use when shaping clay. If life continues evolving into increasingly clever forms, then the next great leap might not be about faster engines or bigger telescopes. It might be about mastering light with so much finesse that whole worlds turn into luminous designs. Picture a civilization advanced enough to wrap an entire planet in reflective materials, transforming it into a colossal cosmic mirror. Such a world would glint like a jewel against the blackness of space, catching starlight and redirecting it toward distant outposts or energy collectors. This planetary mirror could act as a beacon, signaling across light years with patterns only another advanced civilization would recognize. Even more creatively, they might shape this reflective shell so it focuses light onto specific regions within the solar system, like a magnifying lens on a celestial scale. Instead of relying on sunlight directly, smaller colonies or habitats could receive concentrated beams of illumination from their mirrored neighbor. The planet would not simply exist, it would perform. This kind of structure would not be made from simple glass or polished rock. Future engineers might craft materials that reflect only certain wavelengths, forcing the planet to shimmer in coordinated colors. Imagine a world that glows blue on one side and gold on the other, shifting hues as it rotates. It would be a giant cosmic disco ball, one with scientific precision and artistic flair. It could modulate its reflectivity on a schedule, sending encoded pulses of colored light into space. Perhaps these signals would be used for communication, or perhaps, in a very future sense, they would be used as art, messages painted not on canvas, but on the surface of a planet. But planetary mirrors are only one possibility. Advanced civilizations might also build immense structures that manipulate light with extraordinary control. Think of orbital networks of thin, lightweight sheets engineered to catch starlight like sails. These light sculptures could be arranged into patterns or shifting forms that dance across the sky. As the sheets tilt or rotate, they would redirect beams of sunlight, painting radiant shapes across space itself. Travelers approaching the system might see loops, spirals, or flowing ribbons of brightness, an astronomy-inspired ballet of photons. At an even grander scale, a civilization might decide to build structures that curve light the same way gravity does, but intentionally. Instead of relying on massive objects to warp space, they might construct megastructures designed to bend beams into arcs or halos. These installations could behave like engineered gravitational lenses, controlled distortions that magnify distant galaxies or funnel light toward remote observatories. Instead of waiting for cosmic luck to give them a natural lens, they could build their own. They would literally sculpt starlight into useful shapes. More imaginative still is the idea of light farms, where future societies cultivate beams like crops. These farms might be vast arrays that collect starlight from multiple directions, channeling it into storage nodes where photons are preserved, filtered, and re-emitted on command. Energy, illumination, and communication could all be orchestrated from these glowing fields. Light would become something like a harvest, a renewable resource tended, stored, and distributed with the skill of cosmic farmers. Some civilizations might choose to use light not merely for utility, but for cultural expression. They could flood their skies with controlled auroras, weaving curtains of shifting color across their atmospheres. Instead of natural magnetic storms producing shimmering lights, they might have technologies that inject carefully tuned particles into the upper air, creating displays that resemble living murals. An entire civilization could celebrate festivals by illuminating their sky with colossal, orchestrated waves of green, violet, and amber. Imagine visiting a world where the night sky blossoms like a flower. Even stranger possibilities unfold when considering artificial stars. Future engineers might ignite small fusion spheres or controlled plasma clouds that glow with specific wavelengths. These artificial suns could be used to warm distant colonies or illuminate worlds orbiting dim stars. They might even be arranged into patterns, turning regions of space into deliberately designed constellations. A cluster of glowing orbs could act as a cosmic compass, guiding travelers or marking the boundaries of a civilization's domain. Light, in this future vision, becomes architecture. One of the most ambitious concepts is the idea of a civilization building structures around entire stars. Shells, swarms, or vast lattices designed to capture nearly all the starlight and re-emit it in selective ways. Instead of a simple sphere meant to harvest energy, a future society might build a star-encompassing sculpture that beams light outward in carefully constructed shapes. From afar, the star would not shine as a point, but as an intricate pattern, broadcasting an unmistakable signature into the galaxy. Two entirely different civilizations might even communicate by adjusting the geometry of their stellar structures, light as language, star as speaker. Imagining these possibilities reveals something profound. Advanced civilizations may not be satisfied with simply using light. They may aspire to shape it, choreograph it, and let it become part of their identity. In our own era, we use light to illuminate streets, display images, and send messages through digital networks. But in the future, light might become an artistic medium, larger than continents, larger than planets, a medium that spans space itself. The universe is already beautiful, but future civilizations may decide to make it even more so, finding new ways to recycle light into creations that blend science, culture, and pure imagination. If humanity someday joins them, we might look up not at stars alone, but at wonders crafted from light, cosmic masterpieces crafted by civilizations who learned that photons are more than particles. They are possibilities waiting to be shaped. If you step back far enough, mentally at least, since the physical version would require an intergalactic spaceship with very optimistic fuel estimates, you begin to see the universe not as a collection of separate phenomena, but as a vast interconnected choreography where light plays the lead role. It is easy to think of starlight as something simple, a glow in the sky, a warm patch on your skin, a visible thread across the darkness. But when you follow that glow through all the stages of its cosmic journey, you begin to notice something remarkable. Light is not a visitor that briefly illuminates the universe and disappears. It is a worker in an endless cycle, a traveler whose job never really ends, a storyteller that keeps getting recruited into new roles. In this cosmos, nothing is wasted. Not heat, not matter, not even the smallest flicker of a photon. Think about where light begins, not in open space, but deep within stars where conditions are so extreme
They make volcanoes look like scented candles. There, light is born in chaos, but ultimately escapes with determination bordering on heroic. It does not merely leave a star, it graduates from the most intense training program in the universe, and the moment it reaches space, it becomes something new, a messenger carrying the signature of its birthplace, racing outward to places it never could have imagined. The universe does not simply emit light, it dispatches it like cosmic mail. Along the way, light encounters landscapes and obstacles that challenge its straight-line instincts. Gravity bends it, stretching it like a cosmic gymnast. Dust clouds catch it, scatter it, and turn it into glowing murals. Ancient radiation hums through space, a fossil of the universe's beginning, stretched thin but still present. Black holes twist and repurpose light in ways that border on absurd. Some photons are trapped, some are stretched, and some get flung away in spectacular jets that scream across intergalactic space like fired arrows of radiation. Galaxies absorb and reuse light, melting it into the rhythms of star birth and star death. Planets use it to sculpt climates, swirl winds, and carve out ecosystems. Life itself, quiet, sophisticated, improbably clever, learns how to store light inside chemical bonds, turning photons into food, fuel, and eventually entire forests. Light becomes the foundation of food chains, the architecture of growth, the spark behind every green leaf that ever fluttered in a breeze. Humans, never content to sit back and admire, join the recycling symphony by harnessing light in ways both practical and poetic. They build panels that catch photons and convert them into electricity. They weave cables that guide light like racing messengers. They design tools that sharpen light into surgical precision or broaden it into information displays. In the human world, light becomes currency, communication, entertainment, measurement, and invention all at once. And when imagining the future, when imagining what civilizations might do with 10,000 more years of cleverness, light transforms into something even more ambitious, sculptures that span worlds, signals written across stellar surfaces, structures that bend light into shapes the universe has never naturally produced. Civilizations might someday converse not with radio waves or wires, but with the very glow of their stars. Photons might become building materials for art so grand it can only be admired from space. What all these threads reveal is a cosmic truth that is surprisingly comforting. Light is never wasted. It might travel for billions of years, scatter into clouds, bend around planets, pass through leaves, tunnel through fiber optics, or be swallowed by a black hole's gravitational embrace. But in all these transformations, light continues to matter. It becomes warmth, motion, growth, information, and even memory. It marks time across ancient distances, carries stories across the dark, and stitches together the fabric of cosmic history. Even when a photon meets its supposed end, absorbed by a leaf, captured by a solar panel, consumed by a dust grain, or caught forever by a black hole, it is not truly gone. Its energy persists. It becomes part of something else.
It nudges electrons into motion. It heats a patch of soil. It fuels a chemical reaction. It gets woven into the glow of a nebula or the rhythm of an ecosystem. In this universe, endings fold gracefully into beginnings. The recycling is relentless and deeply elegant. This is what makes the cosmos feel alive, not in the biological sense, but in the sense of constant renewal. Everything interacts, transforms, and reappears. Matter becomes stars. Stars become dust. Dust becomes planets. Planets breed life. Life captures light. Light travels on, whispering the history of all it has touched. There is no final destination for energy, no cosmic trash heap where discarded photons gather. Instead, there is an endless exchange, a grand conversation played out across billions of years. So when you look at the night sky, remember that the light reaching your eyes is not just illumination. It is resilience, it is transformation, it is history given form. The glow of a distant star, the shimmer of an aurora, the warmth of a sunlit afternoon, all of it is second-hand energy, passed through countless hands, shaped by countless journeys. The universe does not waste light. It reassigns it again and again, ensuring that even the smallest photon gets its chance to contribute to the story. And in witnessing that cycle, we glimpse the astonishing truth. We live in a cosmos where nothing is lost, where every spark matters and where light in all its forms always finds a way to shine again.